Assalamu alaikum, everybody. Welcome to our lecture number 8 for the course Introduction to Artificial Intelligence. This lecture is titled Probabilistic Reasoning, and it is basically an extension of the last lecture where we laid down the basic concepts of probability, and now we're going to see how to apply those concepts to represent knowledge in an uncertain domain. This is the outline of the lecture. First, we show how knowledge can be represented in an uncertain domain using what is called Bayesian network. Then we look at the semantics of Bayesian networks. And then we look at the compactness of Bayesian networks in terms of saving space compared to the normal full join distribution. And then we look at exact inference in Bayesian networks. And finally, approximate inference in Bayesian networks. So let's start with the first topic, representing knowledge in an uncertain domain. And so far we have seen that full join distribution can answer any question about the domain, but it can become too large to represent as the number of variables grow. And then we saw that independence and conditional independence can greatly reduce the number of probabilities that need to be specified and stored in full join distribution. We learned all of this in the last lecture. We're now going to introduce Bayesian network, which allows us to again represent this full joint probability distribution in a more compact manner. As we shall see, Bayesian network is actually a data structure that is used to represent dependencies among variables. Bayesian networks can be used to represent any full joint probability distribution, and it will be able to do so concisely or compactly. So what is a Bayesian network? A Bayesian network is basically a directed graph in which each node is annotated with quantitative probability information. The full specification for a Bayesian network is as follows. Each node in the graph corresponds to a random variable, as you can see in this simple example that we have been following. So cavity, weather, toothache, and catch are examples of variables, random variables, and they are represented as nodes in the Bayesian network. And then a set of directed links are used to connect pairs of nodes, such that if there is an arrow from node X to node Y, we say that X is a parent of Y. For example, here, cavity is a parent of both toothache and catch, which is also interpreted to mean X influences Y. X influences Y. It is cavity that will create toothache, or that will cause toothache. It is also cavity that will cause a catch. Okay, so that's why we also have another way to interpret the link as X causes Y. So if there's an arrow between X and Y, it can be interpreted to mean X causes Y. So this is how the graph is represented. The graph has no directed cycles, so it is a cyclic graph, as otherwise known as DAG. Each node xi also has a conditional probability distribution, probability of xi given the parents, that quantifies the effect of the parents on the node. We're not showing the conditional probabilities on this simple example, but we will show it in the next one. Now, once the topology of the Bayesian network is laid out, the next step is to specify a conditional probability distribution for each variable given its parent. So let us consider the following relatively more complex example compared to the dental problem example. Say you have a new burglar alarm installed at home. It detects burglary, but it also responds to minor earthquakes. Now you have two neighbors, John and Mary, who have promised to call you at work when they hear the alarm. Okay, so if your alarm sounds off, John and Mary promise to call and inform you. Now John nearly always calls when he hears the alarm, but sometimes he confuses the alarm with a telephone ring. So if a telephone ring in your house, John sometimes thinks that is the alarm, and therefore he calls even in that case. Mary, on the other hand, she likes loud music, and therefore sometimes she misses the alarm because her loud music will not allow her to hear the alarm. Now, given the evidence of who has or who has not called, we would like to estimate the probability of burglary. The Bayesian network for this scenario is shown in the next slide. So this is the Bayesian network for the scenario we have just explained. As you can see, there are 5 nodes in this Bayesian network, where each node represents the random variables. So we have burglary, earthquake, alarm, John calls, and Mary calls. And clearly the arrows indicates the direction which a variable or which state causes another. Obviously, burglary and earthquake are not influenced by the other variables, so they are like parents in the graph, as you can see. But if there is a burglary, most likely the alarm will sound off. Similarly, if there is a minor earthquake, the alarm will sound off. And therefore there should be an arrow from this burglary to alarm, and also from earthquake to alarm. Now, if the alarm sounds off, the neighbor John will likely call to inform you, and similarly Mary may also call. So there should be a directed line from alarm to Mary and also to John. Okay, now in addition to the graph, as we said, each node is also represented with the conditional probabilities for that particular node. So starting from the top, as we said, burglary is not influenced by any of the other variables. So the probability you see here is actually a prior probability, unconditional probability. Okay, the probability of burglary occurring is 0.001. And similarly for the earthquake, it's a prior probability or unconditional probability, and it is 0.002. Alarm, however, is a conditional probability. Okay, so therefore we have to look at the values of the parent. Okay, so there are two parents, burglary and earthquake, and these are the possible combinations that we can have. Okay, burglary is true, earthquake is true. Probability of the alarm sounding off is 95%. It is 94% if there is burglary, but there is no earthquake. And similarly, it is 0.29 if there is no burglary, but there is a minor earthquake. And finally, if there are no earthquake, no burglary, the alarm may still sound, but with a very small probability of 0.001. So those are the conditional probabilities for the alarm sounding off. For John calls, as you can see, it's purely based on whether the alarm sounds or not. Although we say sometimes John misses a telephone ring with the alarm, so he may call even if the alarm does not sound. So the probability of John calling if the alarm sounds is 90%. For Mary, as we said, she enjoys loud music, so her reliability is not as good as that of John. She calls about 70% of the time if the alarm sounds off. And she calls for 0.01 even if the alarm doesn't sound off. Alright, so that's our Bayesian network. So clearly the network structure shows that burglary and earthquake directly affect the probability of alarms going off, as I already explained. But whether John and Mary call depends only on the alarm. Okay, so the conditional distributions are shown as conditional probability tables, sometimes called CPTs. Okay, so these conditional probability tables that we discuss are called conditional probability tables. Now, each row in a CPT contains the conditional probability of the node for a conditioning case. Okay, as we already explained. So this row is showing the probability for the conditioning case where both burglary and earthquake are true, whereas this is for the conditioning case where burglary is true and earthquake is false, and so on and so forth. Now, one thing we're not showing in this table is this, that each row must sum to 1 because the entries represent an exhaustive set of cases for the variable. But as you can see here, the sums are not up to 1. So what is happening? So actually what is happening is we are missing something on these tables, which is the not cases. What is the probability of the alarm not sounding off? We are eliminating it from the table because actually we can drive it. Probability of not A. Okay, and similarly here there will always be another column to indicate the not cases or the false cases. The point is, for a Boolean variable, if the probability of a true value is P, then that of false can be calculated automatically, and it is 1 minus P. And therefore there is no need to have to save it in the table. Okay, this is simply going to be 1 minus 0.95, which is 0.05, and so on. So there's no need to store these values because they can be computed, since they can be computed from the other values. Okay. A node with no parents has only one row representing the prior probabilities of each possible value of the variable. As I already explained, burglary and earthquake, they do not have any parent, and therefore their probabilities here are prior probability or unconditional probabilities. Alright, semantics of Bayesian networks. How should we actually interpret these Bayesian networks? There are two ways in which one can understand the semantics of Bayesian networks. The first is to see the network as a representation of the joint probability distribution, similar to what we have been seeing before. And the second view is to understand it as an encoding of collection of conditional independent statements. As we saw there, the nodes are arranged such that the children are always influenced by the parents, and therefore the probabilities of the children are conditional probabilities given the probabilities of the parents. So this is another way to look at those. The two views are actually equivalent, and we shall see that in a moment. But the first one is helpful in understanding how to construct the network. Okay, if you are given a certain domain, looking at the network from the point of view of joint distribution will allow you to actually construct the network. Whereas the second view is helpful in designing inference procedures. Okay, if you want to determine a particular probability given some of the information already in the network, then looking at it from the point of view of conditional independence will allow you to come up with the procedure for the inference. Again, we shall see that in a moment. Now, we will use the following abbreviation as we try to define the meaning or the semantics of a Bayesian network. We shall use P of x1, x2, and so on until xn to mean the probability of x1, the random variable x1, being assigned the value small x1, and x2 being assigned the value small x2, and so on. So this is how we should interpret this notation. We shall also abbreviate parents of a node xi as this. So parents of xi, meaning the value of the parent of xi. Now, from a Bayesian network, we can always calculate P of x1 and so on until xn by simply multiplying the individual conditional probabilities of the nodes. So it's going to be probability of x1 given the parents of x1 times the probability of x2 given the parent of x2, and so on and so forth until we reach n. So for the product of for I from 1 to n of the probabilities of xi given the parent of xi. This is the actual meaning of the Bayesian network, how to compute the probability of x1 and x2 and so on until xn. I shall show how we derive this formula in the next slide. And this is actually the derivation. We know from chain rule that probability of x1, x2, and so on until xn is the same as probability of xn given xn minus 1 until x1 times the probability of xn minus 1 until x1. This is from the chain rule. Now we can recursively expand this one again. So instead of probability of xn minus 1 to x1, we can have probability of xn minus 1 given probability of xn minus 2 to x1 times the probability of xn minus 2 to x1. So again, we can continue to expand using this chain rule until we reach just x1. And this expanded representation is basically a product of the individual terms, where I ranges from 1 until n. So it is going to be the product of the probability of xi given xi minus 1 until x1, where I varies from 1 to n. Now we are saying this term is actually equivalent to the product of xi given its parents. We shall see why these two are equivalent. Why is this equal to this, especially for a Bayesian network? This is true for any sequence of probabilities, whether for a Bayesian network or not. Okay, P of x1 to xn, just using pure chain rule, we can reach up to this point. Okay, so this is not necessarily related to Bayesian network. This is general. P of x1 to xn, just by applying chain rule, we are able to show that it is equal to this. Okay, and now we are saying, but this, for the particular case of Bayesian network, is actually equal to this one, probability of xi given its parent. So this can be equated with the parent of xi. We shall look at this more closely in the next slide. Why is that so? So why is probability of the product of P of xi given the rest of the x equal to the product of probability of xi given the parents of xi? So for this to be true, we need to do two things. One is the parent of xi. The parent of xi must be subset of the variables, the random variables xi minus 1, xi minus 2 until x1. And this can be easily done just by labeling the nodes according to the partial order in the graph. Okay, so this is not an issue. Just number the nodes accordingly so that the parents will always appear first before the children. But more importantly, we need xi to be conditionally independent of its predecessors, given its parent. We need each node xi to be conditionally independent of its predecessors, given its parent. Because if it is, then we can write this to be equal to this. Okay, but this is exactly what happened in Bayesian network. Bayesian networks, as we explained, the nodes are arranged such that the parents appear first, and then there's a link from the parents to the children. And therefore, this again follows automatically from the fact that we are dealing with Bayesian network. And this is why for Bayesian network, these two equations are equivalent. This is the idea. So, and therefore, with that formula, which we call equation 1, we can be able to answer any query regarding the Bayesian network. Let's take two examples here. The first one, what is the probability that all the variables are true? So burglary is true, earthquake is true, the alarm is true, John calls is true, and Mary calls is also true. What is the probability of that? Can we derive that from the information in this Bayesian network? We'll just apply what we have just learned. So probability of JMABE, where JMABE are the abbreviation of the initials of the different variables. So J, as you can imagine, is for John calls, M is for Mary calls, A is for the alarm sounds, B is for the burglary, and E is for the earthquake. So according to what we just saw there, this is equal to the product of the probabilities of each of these variables given its parent. Okay, we said P of x1, x2, and so on until xn is simply the product for I equal to 1 to n of the probabilities of xi given the parent of xi. So this is what we're going to do to compute this. Okay, so this is equal to probability of John calls. Now what is the parent of John? Is alarm, and therefore given alarm. Probability of John calls given alarm, xi given its parent, times the probability of Mary calls. Again, the parent of Mary is alarm, and therefore given alarm, times the probability of alarm. Now alarm has two parents, burglary and earthquake. Therefore, we will say probability of alarm given burglary and earthquake, times probability of burglary. Burglary is unconditional probability, so just probability of B. And similarly for the earthquake, probability of E. So multiply all of this and you will get the probability of all these variables being true. And of course we read this directly from the tables. Probability of John calls is 0.9. Probability of Mary calls is 0.7. Probability of alarm, given that both E and B are true, is this first row here, 0.95. And then probability of burglary occurring is 0.01, and probability of earthquake occurring is 0.02. So just read these values from the given conditional probabilities, multiply them, and you get your answer. So this is the probability that all of the 5 variables are true. And you consider it's a very small probability indeed. Let's take another example. What is the probability that the alarm has sounded, but neither burglary nor earthquake has occurred, and both John and Mary calls? What is this probability? So again, just like we saw there, the only difference is now we have no earthquake and no burglary. So instead of using B and E, we now have to use not B and not E. Okay, so no change in the first 3 products. Probability of J given A, probability of M given A, but there's a change actually in probability of A. It should now be probability of A given that no burglary and no earthquake occurred. So not A and not B. Okay, so this is slightly different than before. Okay, and then probability of not B and probability of not E. Multiply all of this and you get your answer. Alright, now the first two terms are the same as before, 0.9 and 0.7 for Mary calls and John calls, no change. But for the alarm, we are looking for the value for which both the burglary and earthquake are false. So we're actually interested in this row this time. This is the row we're interested in. And therefore our value is 0.001, not 0.95 as we saw before. Alright, so that's the probability of A given not B and not E. Now multiply that with the probability of not B. Now here you have to be careful. Probability of B is given, it is 0.01. We assume you can use that to calculate the probability of not B. So probability of not B is simply 1 minus this. So it's going to be 0.999. Okay, that's what you are seeing here. And similarly for the probability of not E is 1 minus this, which is 0.998. So multiply all of this again and you'll be able to answer that query. So basically with Bayesian network, just like we saw in the last lecture with full join distribution, if you are given any query related to the network, you should be able to answer that query simply by reading the corresponding values from the given conditional probabilities. Let's now talk briefly about the compactness of the representation of Bayesian networks so that you can compare it with the representation of full join probability distribution. So consider n binary variables or Boolean variables. Unconstrained join distribution, as we discussed in the last lecture, will require big O of 2 to the power n probabilities to be computed. However, if we use Bayesian network, let's say a Bayesian network with a maximum of k parents for any node, so no node has more than k parents, then we're going to see that we only need probabilities in the order of big O of n times 2 to the power k. Okay, so obviously if the maximum number of parents is much smaller than the number of variables, and that is usually the case, then definitely the Bayesian network will you only need fewer, you will need much fewer probabilities than in a full join probability distribution. Let's take an example to make sure this idea is clear. Let us take n to be 30. So you have a full unconstrained join distribution with number of random variables to be equal to 30. So clearly in that case you will need in the order of 2 to the power 30 probabilities, okay, to represent, and that is about 10 to the power 9, which is more than a billion. Okay, now compare that with the Bayesian network with the same number of variables, 30, but with maximum number of parents for any node to be equal to 4. Okay, so if you have only 4, 2 to the power 4 is 32, and if you multiply 32 by 30, okay, so n, which is 30 times 2 to the power 4, you will have only 480 probabilities to manage. So clearly this is a huge saving compared to the normal joint probability distribution. From 1,000,000,000 to just less than 100 is definitely a great saving, which shows the importance of this Bayesian network representation. For our example of burglary alarm, these are the number of nodes that you're going to need. Okay, of course, you're going to need one probability for the burglary, one for the earthquake, but for the alarm, you're going to need 4. Okay, because the alarm has 2 parents, and 2 to the power 2 is 4. The John calls and Mary calls, each one will have 2, as we saw there, because each of these has 1 parent, and 2 to the power 1 is 2. So you're going to need 10 different numbers. As we can clearly see in our Bayesian network here, if you count the numbers, they are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the maximum probabilities you need in this Bayesian network. If it were to be a full joint distribution, obviously you're going to need 2 to the power 5 minus 1 probabilities, which is 31. Okay, so that shows you the advantage of a Bayesian network in terms of its representation. We don't need to represent too many probabilities compared to a normal joint probability distribution.